Let us discuss in this video the notion of partial derivatives. Partial derivatives is something we already know. The definition of a partial derivative of a function f from an open set E in Rn into Rm, okay, has partial derivatives respect to each of the variables. And we will denote partial f with respect to xi or df dif. Okay, this is the notation, and the way it is defined at a given point, let's say the point x. Okay, these are both notations, the classical and the modern. The way it is defined is as the limit as h tends to 0 of f of x plus h ei minus f of x divided by h. Okay, and in this case, 8 is a real number. Okay, so we don't need to put absolute values, modulus. Okay, that's important. Here, ei is the vector that has components all 0 except for the position I that has a 1. All right, so here something we need to observe is that the partial derivative of f at xi, okay, the jth coordinate actually at the point x, we can take out the vector. You see here what I'm doing? I'm writing the jth coordinate. Okay, this is the derivative, the usual derivative respect to t at t equals 0 of the function f j of x plus t e I. Okay, so here we are freezing all coordinates except j. Okay, so we can think about it as a 1D derivative. The 1D derivative of the function that results from freezing all coordinates except the ith coordinate. Now, there is a very important connection between the differential and the partial derivatives. So if we have a function like, as usual, I'll just copy f from E open in Rn to Rm. Okay. The differential of f at x is actually, remember, this was a matrix. So this is given by the matrix that has coordinates d1, f1, x, and so on. Then dn, f1, x, and then here we have d1, fn, x, and then here, sorry, m, and then here dn, fm, x. Okay, let's double check. So m is the number of components in the vector in the output. So we have f1 through fm. So here we are good. And then we have n coordinates. So here we are good too. Okay, so we are taking the derivative of the first function in the first row, then all the derivatives, d1 and so on until the end. And then we keep moving down the table. Okay, and this is an important theorem because this is saying, well, of course I omitted lots of things that I should say now. This is not going to work for any function, this is going to work for a differentiable function, okay? Let's say well, in E, differentiable in E. Okay, so then the matrix of df with respect to the canonical basis is given by this matrix that actually has a name. It's called the Jacobian matrix. Okay. Following our notation, we have also denoted this as f prime of x. Okay, so you will see both notations depending where you are reading. So it's important to know both. Now, the most important thing about this theorem, this is saying if the function is differentiable, then the differential is going to be this matrix. So in order to check if a function is differentiable, you can plug in this matrix right away. Okay, because it's either this one or none. Remember, we did an example where I was checking if a function was differentiable, but I said this is more difficult now than it has to be because we have to guess what was the differential. We didn't know back then, but now we know that that differential is given by the partial derivatives. So first thing we need to do when checking differentiability is to check if the partial derivatives exist, and if they do, if the differential given by this matrix of partial derivatives satisfies the definition of differentiability. Okay, that's all we need to do. Now, one more thing I want you to note. The theorem implicitly states that the partial derivatives, no, that if the function is differentiable, then the partial derivatives exist. Okay, this is very important because sometimes we tend to think the other way around, but the other way around is not true. But the other way around is not true. Okay, what I mean by this is all partial derivatives exist does not imply f differentiable. Now, the way to understand this, imagine you have a road, a function that looks like this. You have here 0 and you have the two axes. Okay, and this function somehow is like a bump on the road. Okay, it's like a triangular bump on the road. And you have here the surface of your road. Okay, and then here you have your bump. Okay, and you see this bump, this hole actually, what happens is that it has very straight edges. Okay, these edges just follow the axis. And if you take the derivative, this is your f somehow. If you take the derivative respect to x and the derivative respect to y, both are going to be 0. Okay, do you see why? Because along these lines, the function is constant. Okay, but if you would take a different line, then you would see that there is a discontinuity. Okay, and that's the reason, if you think about this, here the partial derivatives exist, they are both zero, but the function is not differentiable, it's not even continuous. So this is one example of things that can happen. You could say, well, yeah, because you have the picture, yeah, so do I have to plot it to know what's going on or not? No. For example, we can think about f of xy equal xy squared divided by x squared plus 2y to the power 4. Okay, this is if xy are different from 0, 0. And f of 0, 0 equals 0. For a function like this, we can see that it's not differentiable at 0, 0, but the partial derivatives exist. I should probably write 0, 0 here instead of just 0. In fact, I mean, just look at the function. If we take, it's not even continuous. Okay, to check that it's not even continuous, you can try a path that is, yeah, x equals y squared. Why am I choosing this? I'm choosing this because if you see here, they are not balanced. The x has a power of 1, the y has a power of 2, and same in the denominator. Okay, so what I can do is to plug x equal y squared. So here I get y to the power 4, which is the same power as in the denominator. So there will be a cancellation and then it will not work. So f of, xy equals f of y squared y. That is y squared y to the power 4 divided by y to the power 4 times 3. So this is constant equal 3. Okay. But f of 0, 0 equals 0. So the limit as xy tends to 0, 0 of f of xy is not 0. Okay, so not continuous. So if it's not continuous, then it's not differentiable. And this solves the first part of the problem. But then the partial derivatives, here we don't really need to do any computation because see what happens. To find the partial derivatives, we only need to find the derivatives, right? Respect to t, partial derivatives at 0, 0. We just need to find the derivatives in 1D of the function that results from freezing one of the variables at a time. Okay, and this is when t equals 0. Okay, so this is one of them. The other one looks very similar. Only the t is in the other variable. So here I could write 0t. Okay, and what happens here? So this is like writing t0, and this is like writing 0t. But notice that by the definition of f, okay, f of t0 is going to be 0 always. So f equals 0 along the lines x equals 0 and y equals 0. So then the partial derivatives are both zero. They exist, okay? But it's a very similar problem as the one that I was mentioning with the hole on the road, okay? It's just that there is a discontinuity, but along the edges, the function is like a constant. Now, see what happens here. It says, all the partial derivatives exist does not imply f is differentiable. But this sounds a bit like an injustice. There is actually, the problem is that we need to ask a little bit more. Okay, there is a theorem that you can find in the book that says that if you have a function from an open set in Rn into Rm, okay, and you have some point, say x in E. Now, if all the partial derivatives exist and are continuous at x, okay, then f is differentiable at x. And here, notice the key point is that the partial derivatives are continuous. Okay, before we were saying if they exist, that does not imply f is differentiable. But if they exist and are continuous, then it's okay. Because then we prevent that issue that we were talking about from happening. Okay, there will be no case like the one we were discussing. Now, this is a very useful condition, so it has a name. Definition: f is of class C1. That means is of class C1. Okay, that means that if and only if all partial derivatives exist and are continuous. Okay, so notice when we say that the function is continuous, we write only C. You see here, this means f is continuous. But if you write the 1 here, that means that the function is continuous and the partial derivatives are also continuous. Okay, so that's much better. And you may see instead of a 1, some other number, 2, n, whatever. That means that you can keep taking derivatives and they are still continuous, but we are not going to discuss that case.